Right, seems we've got a fairly good turnout to begin with. Can everyone hear me?
Yes, I can hear you.
Okay, great. Right. I'm Andrew Cooper. For those of you who don't know me, I work for Citrix on the Citrix hypervisor team. I'm also an x86 maintainer in Xen. I do various security bits. For those of you who do know me, you might be wondering, hang on, what's he doing not looking after speculative security? Now, in this case, what happened was that I needed a break. Citrix had a 2-day hackathon that it had scheduled for all of its employees, and I happened to have a brand new toy from a hardware manufacturer with support in, so I figured I would spend 2 days trying to work on this. This is about control flow enforcement technology, which is a new extension to the x86 architecture to combat return-oriented programming. One common bit is there's a new exception for it that covers faults under the new architecture. There are actually two bits. Set is split into two separate parts. The first is called indirect branch tracking. This is to combat modifications to function pointers. It works by putting an end branch instruction at the head of every function call that might be approached by an indirect jump. Also for static jump tables for switch statements. To be perfectly honest, there are also other ways of doing this. There are software techniques that get you improved edge reduction as well. An interesting thing about IBT is that it does give you a fairly good guarantee that you're not executing misaligned code. The end branch instructions are 4 bytes long, and which means you've got a 1 in 2 to 32 chance of finding it randomly, traded off against the likelihood of finding a useful gadget following it. But that's one side. I'll mention it here. What we want to talk about is shadow stacks, which is what the rest of the presentation is on. So shadow stacks are a new mechanism to protect against overwriting of a return address. So classic buffer overrun vulnerability in languages like C, because unfortunately it's not very nice to us that way. What happens is the call instructions put the return address on both stacks, and ret instructions check both stacks for whether they match, and you get an exception if they're missing. There are some extensions to the architecture for this. There is the new shadow stack pointer register, which is separate to the regular stack pointer register. It is not encodable in any instructions. It's not a general purpose register like that. You also can't directly modify it. There's a new page table memory type. For shadow stacks, you need some separate properties, and what they ended up doing was reusing an existing encoding that previously had no meaning. So on shadow stack capable hardware, the dirty bit is now an access right and has meaning for read-only page tables. So shadow stacks are a read-only page table that also have the dirty bit set in them. There's a new type of page walk access for this, so there's a new error code. So you can determine whether it was a shadow stack access that caused the page fault in the first place. Another thing that differs from the previous architecture is the idea of shadow stack tokens. There are several of these, and they are a word at the base of the stack. They've got several properties. First of all is the majority of a shadow stack token is its own linear address. This is to prevent attacks where someone can control the page tables and alias stacks over each other. So hardware will detect when an alias has occurred and will and will object to it. Shadow stacks have to be 4 or 8 byte aligned because they're stacks, which means you've got some metadata in the low order bits. Some have a busy bit in them to prevent 2 CPUs using the same stack at once. Also important for FAR calls and returns is encoding the 32 or 64 bitness of your application, so you don't confuse one type of shadow stack for another. There are also a number of model-specific registers for this. You've got user and supervisor set configuration. You've got the shadow stack pointers for each ring of protection, a pointer to the interrupt stack table pointers, and all of this is manageable via supervisor states in the Xsave and Xrestore state. So all in all, looks fairly good. You've also got some new instructions that come with this. First up is read shadow stack pointer. This is quite easy. It reads the value of the hardware shadow stack pointer register and gives it to you in a general purpose register. It's encoded in NOP space, so it will execute with no effect on older processors. And it turns out this property is very useful to determine whether set is currently enabled on your system or not. I'll get to that bit a little bit later. As is fairly common knowledge, where long jump and exception handling are things that you would find in normal execution. So there is an inc SSP instruction for incrementing the shadow stack. This is used to unwind a specific number of words from the shadow stack. Now it takes a value between 0 and 255 in it, which ultimately gives you a stride of 1K or 2K. The reason for this is actually to combat stack clash vulnerability. The processor will perform a stack access both at the current position and the destination position to prevent you being able to underflow your shadow stack by incrementing off the top of it. As is also the case, you occasionally need to go and fix up the shadow stack. So there are new instructions for that, the write shadow stack and write user shadow stack instructions. They take a memory operand and override the paging permissions for them. So you can use these instructions to make a change to a shadow stack. They have a separate enable bit, and the idea is that you don't have them enabled by default. It might be a kind of thing that a debugger would need to do to fix up execution when it's modifying other state. Another thing that user space needs to do is be able to switch between stacks. So we have the save SSP and restore SSP instructions. This needs to be, these can be used by user space. All shadow stacks created need to have a shadow stack token at the base of them before these will work. That needs to be provided by your runtime environment. Of course, the kernel on Xen, the operating system, doesn't have any runtime support. So instead, what we have is the set and clear ssbusy instructions, which are necessary for use around syscall, but also to do with setting up shadow stacks in the first place. Syscall is a weird instruction. It does not switch the stack for you, and this has been the cause of so many privilege escalations in the past. I'm sure it will continue to be so in the future. As a result, what happens in the processor is when you do a mode transition, when you do a privilege transition, the shadow stack pointer gets reset to 0 and the operating system has to restart it from the intended position. At that point, we should probably look at Xen's stack layout. So Xen x86 has a stack per CPU, and this is per physical CPU, not per virtual CPU, which is quite different to how most other systems work. What we have is 8 frames which are aligned. order 8 allocation, which allows you to easily access the top of stack block by taking your stack pointer and anding some bottom bits into it. Xen does not use FS-base and GS-base for thread local storage because PV guests use that, and Xen needs to use something different. And it turns out that this has actually saved us from a large number of privilege escalation corner cases, so we like that. Anyway, this diagram shows what Xen's stack layout used to be before. We have 8K of primary stack, a guard page below that to detect stack overflows, and 4 interrupt stack table entries. This is the mechanism that the 64-bit architecture uses to force a stack switch even in 64-bit mode. Double fault is a last-ditch attempt to get some useful debugging out. The other 3 exist in this form only because of the syscall instruction. Any of those can occur after we have switched from user to kernel privilege, but before switch the stack. So all of these need to be covered specially as a result. It turns out that we managed to fit the shadow stacks in without changing the layout too much and without changing the size at all. Something to note is that regular and shadow stacks act as each other's guard pages. An out-of-bounds regular access will hit the read-only property of a shadow stack and take a fault that way, whereas an out-of-bounds shadow stack access will take a fault because it's trying to be a write to non-shadow stack memory. Therefore, we replaced the guard page with the primary shadow stack page. Indeed, that's actually configured, to make things simple, that's configured unilaterally, even at the moment. We keep it read-only. We need 1 interrupt shadow stack per regular interrupt stack, so we have 4 of them. The shadow stacks only contain control flow information. You don't spill data to them, so the quantity of data on a shadow stack is rather smaller than a regular stack. So 1 kilobyte shadow stacks leave you a call depth of 127 calls once you've got taken the token into account, and that's more than enough for our fault handlers there. So overall, we managed to get support in for this without increasing the amount of stack memory that we actually allocate, which was nice. So then we get on to some of the interactions with Xen. The first thing to point out is that the shadow stack spec has basically killed ring 1 and 2. Ring 1 and 2 were kind of sunset in x86, even in the 64-bit specification, where most of it got taken out and laid to one side, but it's kept on working well enough for Xen in the 14, 15 years since that came out, but this has properly killed it. The reason is that Xen's setting of shadow stacks also applies to the PV guest kernel, because in the paging architecture, ring 3 is user space and rings 1, 2, and 0 are kernel, are privileged. In the past, we have logic to enable and disable SMEP and SMAP for 32-bit PV kernel. This works, but is racy with NMIs. For SMEP and SMAP, what we do to avoid impacting the kernel is that occasionally it will impact the kernel when we get a race with an NMI, but we can detect that and fix up in the hypervisor. It is not possible to do that with set, at least I don't think it is. We would end up in positions where we tried re-enabling set on entry into the hypervisor in weird contexts, and it's complicated. The other thing that was a big problem was the fact that an IRET to ring 1 versus an iRector 3 differs by three words in the shadow stack, which means that you've got to shuffle your shadow stack on context switch. And all in all, I didn't want to bother trying to figure out if I could make that work. So at the moment, if you have set shadow stacks enabled, then we disable 32-bit PV guests. You can we have an alternative compatibility mechanism called PV shim, which has been working for a while. So backwards compatibility is maintained around there. In reality, if you're still using a 32-bit PV guest, you are burning electricity needlessly at the moment. The performance for them sucks massively. Either switch to HVM or switch to 64-bit PV and your life will get much better. The next thing to note, going back to the speculation theme, is that Repoline is a ROP gadget. Repoline deliberately modifies the return address on the stack to cause the branch predictor to not do something unsafe. Luckily, David Woodhouse and I took this in mind when we were helping GCC build the Repoline protection. So Thunk Extern specifically was a feature put in because we requested it to allow a kernel to provide its own Repoline thunks. We used that on Xen. Even in the initial XSA that went out, because whether you use Repoline or whether you use Elfence Jump or whether you use plain Jump depends on what hardware you're on and what microcode you've got. So we already wanted to be able to switch out the thunk for the most appropriate one on the hardware. In this case, we now have one new case where we say if we're using set, we must use plain Jump. That's fine. It works, and it now compiles. Another big thing is the write protect bit, which is a often forgot part of the x86 architecture. The original 386 paging mode stipulated that supervisor code, so kernel code, could read and write to read-only mappings. It was quickly decided this wasn't necessarily a great thing and people wanted read-only memory to stay properly read-only, so the 486 introduced the write protect bit, which the operating system may set to prevent it being able to write to read-only mappings. With set, if you have a read-only mapping and you write to it, the dirty bit gets set, and suddenly you've got your read-only memory turning into shadow stacks if you write to it. So for that reason, the set architecture mandates that write protect is set throughout all of it. And that would be fine, except that in Xen we make use of this functionality to modify read-only mappings. We have the alternatives infrastructure on boot, and we have live patch during runtime. Both of these cases temporarily disable this control flag to allow us to modify read-only mappings. For now, what happens when set is enabled on boot, we enable it after we've done all the modifications we want. For live patch, we disable during the live patching aspect of it. And we have I've got some plans in the future to make this slightly less gross and hacky than it currently is. The next observation, which is obvious in hindsight and was distinctly not obvious when attempting to implement this to begin with, if you enable a shadow stack whilst you're in the middle of C, you crash very quickly because you've got a regular stack that has a part of a call tree on it, and then you've got a shadow stack with absolutely nothing on it. One option was certainly to try and set all of this up in assembly before we enter C, but that's very complicated for during boot. We actually have a separate phase right at the end of boot where we move from one virtual mapping of the stack to another virtual mapping. It was actually a performance optimization at the time. When we shoot the guard page, when we shoot the mapping for the guard page, it will break the super page, and we want to retain the super page mapping of Xen's data section. So instead, we run it through its direct map alias. So the stack's still in the same location, but the virtual address used for it is different. Turning on shadow stacks at that point actually works quite well, because we've just emptied one stack to continue setting up. The boot processor also does a lot of work for the secondary processors, so much so that it's actually a fairly small bit of assembly to turn that on before entering C. So that was actually quite nice and easy. Another thing we have is a primitive called reset stack and jump. This is essentially long jump, except you don't need to call set jump first because it's implicit based on where it is. So we use this to unwind the current stack. It's the context switching primitive that we use. It unwinds the regular stack. It therefore needed to be modified to unwind the shadow stack as well. We don't expect it to ever be called with more than 255 slots to go, which means we can simplify the assembly to not require a loop over multiple iterations of 255. There's a separate bit of logic that does a similar thing. Speculative mitigation for Spectre RSB is to execute 32 call instructions to prevent an attacker prevent an attacker's poisoned values from being followed under speculation. That needed fixing up as well, but it's trivial. It's always 32 slots. It's quite easy. Next, we get on to the slightly more esoteric end of things. We have a function called enable NMIs. NMIs are a little bit weird. They have a hidden bit of state called the NMI shadow, which is reset on an IRET instruction. Therefore, we need to construct an IRET to self. And what we do in the regular case is to build up 5 words on the current stack, execute an IRET, and our caller thinks it's just like a regular function call. Doing this with the shadow stack's a little bit harder. We've got inc SSP to unwind the shadow stack, but there's no dec SSP. There's no way to add new words to the shadow stack. Well, there is. You can execute call instructions. So we have a bit of call-oriented programming in enable NMIs to allow the processor not to fault when it takes an IRET, in this case. So we use 3 call instructions and have to fix up with right shadow stack to turn it into a shadow IRET frame. It's also worth noting that this will destroy any call and return speculative optimizations. It will have the same performance hit as REPLines will generally across the code, so it's just something we're going to have to live with, unfortunately. Enable NMIs is fairly rare. We use it during boot and on Intel hardware where we take a VM exit due to NMIs. So it's not a massively common thing. Another big thing that was a problem was exception table support. So one thing we do commonly is to execute an instruction and cope with a fault if it exists. So read MSR safe, write MSR safe would use this to catch the case where it wasn't safe. What we do is in the GP fault handler, we modify the return address. And the shadow IRET frame needs an equivalent fix-up to go along with that. Once those are in place, it all works rather well. Completely unexpectedly, whilst doing this, I found that one IO emulation stub was genuinely using return-oriented programming to function. When DOM0 is talking to the SMM handler, some firmwares use a mailbox in DOM0's general purpose registers. So what happens is DOM0 traps into Xen, Xen emulates, but we need to emulate with DOM0's registers for the DOM0 driver to be able to talk correctly to the SMM handler. and I have fixed that up not to use return-oriented programming. Of course, this is a brand new bit of the architecture. It does come with some rather interesting corner cases that are a little unexpected. An IRET to ring 3 does a lot of checks on the shadow stack, but one thing it explicitly does not fault for is if it failed to clear the busy bit in the supervisor token. This is slightly weird, but according to some CPU architects, it is deliberate. What will happen in this case is user space will start. So in the case that we have an error in Xen and we get a stack underflow or don't unwind enough, user space will continue. User space will start executing, and the next interrupt or exception will suffer a double fault. It's a bug in Xen. The system is going to crash anyway, but it's a very unhelpful way of discovering that you made a mistake several hundred microseconds before, and you've lost any ability to figure out what may have led to the mistake. That said, Xen's interactions here are fairly simple. I hope that will never show itself up. Another thing to note is that for normal operating system functionality, we require right shadow stack to be enabled. For now, it's enabled unilaterally because that was easier. Reducing the scope is something I want to do. I have some plan for it, but it's moderately complicated. You need to do a double write to MSR set to enable and disable it, and it also needs to be NMI safe, which isn't totally trivial to do. So that's work for a future time. Another often overlooked part of x86 is that the instruction stack mechanisms do not work with reentrancy. Both the NMI and the machine check handler do not have atomic ends to their handlers, and in Xen we just blindly assume it never happens, and this is probably bad, and we should do something to fix that. Linux has a bit of a bigger problem because perf is available to user space, which means unprivileged code can easily control when and where NMI is hit. So they have found real bugs from this. There's some insanely complicated logic to detect this case and unwind the stack safely, but it involves exiting from the nested handler directly out to user space, and that is not compatible with shadow stacks in their current form. I do not envy the task of whoever has to try and figure out how to fix that one up. Back when the K6 and the Pentium 2 processor were coming along, it was decided that int80 was a slow mechanism for doing system calls, so Intel went off and invented sysenter, and AMD went off and invented syscall, and between the two of them, they have two half-working instructions. Unfortunately, neither of them work sensibly in isolation. However, the bit that sysenter got right that syscall did not was that sysenter switched the stack from a user to a kernel transition. However, in the set architecture, it does not switch the shadow stack for you, which was a bit of a surprise, a bit unexpected to see. And what it does is it basically means that sysenter now has all the same bugs that syscall has when it comes to handling of the asynchronous exceptions, which means that if you're using set, you are forced to use interrupt stack tables for safety, even in a case where you have arranged not to use syscall in the first place. So that's slightly disappointing to see. The other thing is that switching supervisor shadow stack is very hard to do. The supervisor token is not compatible with the restore token because the busy bit and the 64-bit segment bit overlap. Luckily, we only need to switch it to an empty supervisor shadow stack at the moment, but that is liable to change as we try and fix some of the reentrancy problems above. So it functions for now, but again, it depends on the IST for safety in the asynchronous cases, and it's currently an open question to figure out what to do about that. So overall, all of this code has been accepted into Xen 4.14. To the best of my knowledge, Xen 4.14 will be the first software release to support supervisor shadow stacks anywhere in the world, which is great. You do need a newer tool chain for it, but support for the instructions has been around for a little while in binutils and a little while in LLVM, so it's nothing bleeding edge at the moment. If you want to play with it, check that config Xen shadow stack is enabled. At the moment, it is out with tech preview status. I think it functions correctly, but of course, me testing it on my own is not a great wide range of testing. So it will have to wait a little while before hardware becomes available. It also currently disables Repoline. This, in practice, needs reconciling with some of the hardware spectre mitigations that Xen doesn't fully support yet. So there's some work there to maintain speculative safety whilst also using shadow stacks. As I said earlier, I plan to rework the text patching logic to avoid avoid clearing the write protect bit. It also became apparent throughout this work that Xen's code for describing its stack is actually quite fragile. There are a lot of constants. There are a lot of open-coded things that you can get subtly wrong and not notice. I do have a proposed series that I'm working on that will express that in a rather nicer way, so that will hopefully be generally received. Also, attempt to reduce the areas during which the right shadow stack instruction is usable. That will depend largely on performance testing. I have no idea how much of an impact it will have. But anyway, that's a few small plans for the future. But like I said, it's there in Xen 4.14 and generally usable. And with skating 2 minutes over time, does anyone have any questions? I suppose it's only closing remarks. So for return-oriented programming, yeah, in reality, hardware mechanisms and software mechanisms can generally be used together. CFI tends to depend on a lot of link time optimization to make it usable, and link time optimization is just not in a good enough state right at the moment. If you look at the the LKML threads, there have been a lot of cases on ARM where LTO have been breaking pointer dependency chains that are required for speculative safety. So, yes, in the long term, we would like to use all the techniques available. At the moment, I don't think CFI is in a usable enough state for this at the moment. So the PAX wrap still suffers from the same problem. It can be done without link time optimization, but the overhead is actually quite high for that. So the overhead ends up being quite high because of what you need to exit out. The everything is based on the type of the function, and there are quite a few cases in Xen where we deliberately change the type of function pointers to make them more usable. Things like the system call table, for example, the hypercall table. A lot of the stub function calls as well are basically cast to void before use. So the overhead is not just in terms of the extra code. The extra code, once you've calculated what the type hashes should be, isn't too bad. I fully admit that. The overhead in terms of making Xen compatible with that is liable to be. That's not to say we shouldn't try and make ourselves compatible with it. I think that would be a good thing to do long term. Just remember that at the beginning of this, I did say I did shadow stacks because I wanted a break from other things, and it was actually a moderately easy challenge to have a go at. So that's as much the reason for doing it as anything else. Right, okay, that's a fairly deafening silence on the rest of the questions, in which case, thank you very much for coming and listening, and I guess see you at the virtual pub later. Oh, to answer Connor's question, yes, it does. The way VTX does it is weird. You end up in a position where you run with the guest kernel's PL0 SSP in context, which, as far as I can tell, means it's unsafe to ever switch shadow stack in hypervisor context. I have raised this with Intel. I haven't had an answer yet.